Hello, and thank you for attending my presentation today, Database System Requirements to Achieve ADAS Level 3 or higher. Today we'll take a brief look at some of the types of data that an ADAS must ingest, analyze, and act upon. But I presume if you're watching this presentation, you're probably working on an ADAS system and are already pretty familiar with this. We'll focus most of the presentation on why an ADAS needs a real-time database system and what is and what isn't a real-time database system. Surprisingly, it isn't as straightforward as you might think. Consistency is an important topic for database system vendors. Real-time adds a new aspect that we'll examine. And there are different scheduling algorithms for database transactions in a real-time database system. We'll take a look at two of those algorithms, highlight how they affect the execution of transactions, and how to use that information to select the best algorithm for a system's execution pattern. A key tenet for real-time database systems is deadline management. Transactions must complete within preset deadlines, so we'll look at how that's implemented. Lastly, we'll explain why a real-time database system must, or at least should, operate in a real-time operating system. An ADAS-equipped car is outfitted with many sensors of many types: sonar, LiDAR, radar, optical cameras, GPS, and more. These sensors support functions such as traffic sign recognition, lane keeping, lane departure warning, adaptive cruise control, parking assist, blind spot detection, collision avoidance, and beyond. Let's not forget the internet connectivity required for traffic data, maps, and roadworks. Further, the view that these sensors collectively provide is not static. For example, a car traveling slowly in the city will collapse the information bubble to emphasize points of interest, intersections, and such. Conversely, a car traveling faster needs to look out farther ahead, and for path prediction, for example, shouldn't be overly concerned about intersections ahead that the car cannot navigate kinetically because of the nearness of the intersection and the car's speed. At its core, this is sensor data fusion. All of this data needs to get to a central location, a database, so that it can be aggregated, correlated, analyzed, and acted upon, all in real time. Many of these subsystems are time critical, such as collision avoidance, distance keeping, and path prediction. The logical extension of this is that the database system must be real time. So let's examine what real-time database means. The terms mission critical and real time are often used together. However, they are orthogonal. An advanced driver assistance system is both real time and mission critical. On the other hand, a system that handles financial transactions is mission critical, but not real time. Were it to fail, the result could be financial losses. However, there isn't any time interval in which a transaction must complete, so it isn't real time. Lastly, the control software that runs a print head on an inkjet printer is real time, but it's not mission critical. If the appropriate amount of ink is not deposited in time, you'd end up with a spoiled page, but no one's going to end up dead. Don't fall into the trap of confusing fast and real time. To be honest, embedded database system vendors have done a disservice in this regard, promoting their really fast database systems as being suitable for real-time systems just because they're really fast. When we talk about real-time, we need to be talking about real-time as in deterministic, because real-time is not the same as real fast. Speed is not the most important metric for real-time systems like ADAS. Deterministic response time is. Speedy response is desirable, but speed alone does not guarantee timely response from a database system. For the same reason that real-time operating systems are used for ADAS, a real-time database system is needed. This slide attempts to illustrate this. In this illustration, with a conventional, in other words, not a real-time database system, the real-time task completes the first couple of steps at the 5 and 10 millisecond marks respectively. Then at step 3, the task makes a call to the database runtime. However, the database runtime has no awareness of a deadline and doesn't return control to the task until the deadline is well expired. The system has failed. Here's the thing. In real-time systems, there's a line in the sand with consequences. The line in the sand is the transaction deadline. Crossing the line means the transaction was late, so the real-time system was not able to respond to an event in the real world within the predefined timing constraint. In an advanced driving assistance system, perhaps this means that an accident was not avoided. For non-real-time database vendors that rely on speed to stake their claim in real-time systems, speed is a figure of merit. nothing more. In fact, a real-time system isn't necessarily fast in whatever subjective way you want to measure speed. A real-time system is deterministic. In contrast to real-time systems with high-throughput systems, there isn't a separation between acceptable and unacceptable. A late answer is still a valid answer. Again, speed is meritorious, but not especially important except for bragging rights. To belabor the point a bit more, in recent years, the term real-time has been abused by database vendors that have nothing to do with real-time systems. For example, Redis's homepage proclaims it to be the world's most loved real-time data platform. Google claims that the Firebase real-time database is a cloud-hosted database, and that's just a built-in contradiction. What these vendors really mean is that they support acting on live data. The database industry used to use the term active queries to mean query results or analytics that automatically updated as data streamed into the database. This is in contrast to having to pull the database, in other words, having to re-execute a query to refresh the result set. To avoid confusion, the industry should get back to terms like active queries and live analytics. So if those systems are not real-time, then what is? Well, let's go back to the bullet from a previous slide. Real-time software is software that is considered to have failed if a timing deadline is not met. Ipso facto, a true real-time database system must enforce timing deadlines, which in this case means that transactions must complete, meaning that they must successfully commit or successfully abort within a preset deadline. Transactions can never be late. Well, I keep talking about transactions, so now it's necessary to define what a database transaction is. A database transaction is a logical unit of work that must be applied to the database in its entirety or not at all. In other words, it must be applied or not atomically. So a database transaction is not necessarily a single operation, though it may be. In other words, a sequence of operations, such as looking up one record, deleting 5 related records, and updating a field within the original record, must all succeed or fail together. Likewise, a single update or delete command that affects 1 or 100 or 1,000 records must succeed for all or for none. Transactions are usually bound with explicit start and commit commands, or rollback or abort as the case may be, that define the transaction block. Although in SQL database systems, each SQL statement can be treated as a standalone transaction. Most database systems adhere to what are called the ACID properties, where ACID is an acronym for atomicity, consistency, isolation, and durability. Atomicity was just described, that a transaction is applied in an atomic operation. Consistency means that applying a transaction to the database moves the database from one internally consistent state to a new internally consistent state. Isolation means that changes that one task is making to the database cannot be seen by any other task until the first task commits the transaction. Lastly, durability means that once a transaction is confirmed as committed to the database, it is permanent. A real-time database system must enforce an additional type of consistency, that the contents of the database are temporally consistent with the real world, which we call external consistency, within some predefined time limit. To summarize, non-real-time database systems usually enforce internal consistency. There's some exceptions. 2 alternatives to ACID are BASE and the CAP theorem. BASE is an acronym for basically available, soft state, eventually consistent. The CAP theorem stands for consistency, availability, and partition tolerance, and the theorem holds that in a system that implements the CAP theorem, you can have any 2 properties, but never all 3 properties. So with CAP, consistency may be the property that gets sacrificed. BASE and CAP are intended to provide greater scalability than ACID. This assertion is hotly debated in the database industry, but one thing is certain. BASE and CAP were born out of old-school relational database systems' difficulty with scaling out. The debate revolves around whether or not that's still the case because relational database systems have evolved. A real-time database system should, but is not required to, enforce internal consistency just like any other ACID database, but it must also enforce external consistency. Performance is measured by the ratio of transactions that meet their deadline, in other words, are successfully committed, to the number of transactions that miss their deadline, in other words, are successfully aborted before the deadline, but no transaction should ever be late. Developers of a real-time database system need to architect the system in such a way that it can guarantee that a transaction will never go past its deadline. To accomplish this, the database system developers need to be able to inform real-time system developers when a transaction has to be aborted in order to meet the deadline. We did this by implementing a new transaction abort procedure that allows us to guarantee that the time required to reverse any modifications made within a transaction up to a point in time will not exceed the time required to apply those same modifications. That in turn allows real-time system developers to use a simplistic calculation to determine the point at which a transaction must commit or abort to meet the deadline, which is simply T2 divided by 2. There's a much more elaborate dissection of this that we don't have time to go into in today's short 20-minute presentation, but if you're interested, please contact me and I'll share it with you. So let's break down the timeline of a transaction. A transaction begins when the application code invokes it. If the database system is busy with one or more other conflicting transactions, the newly created transaction will be putting into a waiting queue, but the clock on its deadline has already started. It's conceivable that a transaction will time out without ever getting scheduled for execution. Of course, you want to avoid that. Once scheduled, the transaction begins executing, and we call this the workload interval. The database runtime cannot be a black hole from which emergence is indeterminate, as we saw on the previous slide. What I mean is when the system makes a call to the database runtime, the task can't disappear inside the database runtime for an indeterminate amount of time, possibly blowing right by the deadline before the database runtime returns control to the application. The database runtime needs to be aware of the deadline and be constantly looking at the clock and be able to return control to the application before it's too late to abort the transaction and allow it to finalize before the deadline. These are shown as deadline verification checkpoints. At some point, the transaction must commit or abort to allow the database runtime to finalize the transaction before the deadline. Therefore, a real-time database system must monitor the progress of the transaction and forcibly abort it when it can be determined that it's necessary in order for the transaction to complete before the deadline. This is the deadline control point. Remember, in a real-time database system, each transaction must complete before the deadline and never be late. Here, complete means meeting the deadline by successfully committing or successfully aborting. The deadline is set by the application and passed as a parameter to the transaction start command. It's up to the system developers to assign the deadline. A rollback mechanism that guarantees that the time to roll back a transaction is not greater than the time taken to apply the transaction up to a point in time allows a simple means of determining the transaction deadline. It's simply half of the real-world deadline, or T2 divided by 2 on the earlier slide. In reality, aborting a transaction can be substantially faster than the time taken to apply the transaction up to a point in time. So half of the real-world deadline is a worst-case scenario that can be adjusted based on empirical data that you collect during testing and simulations. The transaction scheduling policy has an impact on the ratio of completed to aborted transaction. So let's explore two such policies. The first will be high priority, earliest deadline first, which I'll simply refer to as EDF because that's just a mouthful. The second is priority inheritance, with EDF, transactions are scheduled according to priority and within the same priority by the earliest deadline. The transaction's priority is another parameter that's passed to the database runtime through the transaction start command along with the deadline. With priority inheritance, transactions are scheduled that have the same priority in first in, first out order without regard to their deadlines. Before we get into the differences between priority inheritance and EDF, let's summarize the mandate of the transaction scheduler. First and foremost, it must enforce the transaction deadline and then attempt to maximize the number of tasks that successfully commit their transactions relative to the number of tasks that have their transactions aborted. Remember, that's the metric of success for a real-time database system, the ratio of the number of tasks that successfully commit their transactions to the number of tasks that successfully abort their transactions. The best way to illustrate the difference between the EDF and the priority inheritance schedulers is to examine use cases. This is an exercise that real-time system developers should go through in any case. Suppose we have 3 real-time tasks. HDB is a high priority task that wants to write to the database. M is a medium priority task that doesn't work with the database at all. LDB is a low priority task that also wants to write to the database. So in our scenario, LDB starts a transaction first. After that, M comes in, and because it has a higher priority, it preempts LDB. But LDB still has the database, even though it was preempted because its transaction is still active. Next, HDB arrives, but it's unable to start a transaction because LDB has the database. The highest priority thread, HDB, will have to wait until the lowest priority thread, LDB, completes its transaction, which in turn has to wait for M to yield. Consequently, by the time HDB gets the database, it doesn't have sufficient time to complete its transaction before its deadline. However, with priority inheritance, shown on the lower half of the slide, the operating system will be able to raise LDB's priority up to HDB's priority at the moment when HDB arrives, thus allowing LDB to preempt M, which allows LDB to complete its transaction and free the way for HDB, and all transactions meet their deadlines. As you can see in this scenario, the priority inheritance scheme is better. So let's look at a scenario in which EDF is superior. Again, we have 3 transactions, in this case, all with the same priority. The picture illustrates a scenario in which 2 transactions have arrived, while another transaction, the lowest one, is executing. In this scenario, the priority inheritance scheduler would execute all 3 in the order in which they were registered with the system. In other words, first in, first out. Yet it's possible that the deadline of the 3rd transaction, the highest in the picture, and its deadline is T1, is sooner than the deadline of the 2nd transaction, which is shown as T2. Consequently, the 3rd transaction gets scheduled too late to complete before its deadline. With the EDF scheduler on the lower half of the slide, the 3rd transaction will be scheduled to run before the 2nd transaction, even though it arrived in the queue after the 2nd one, because its deadline is earlier than the 2nd transaction's deadline. As a result, all the transactions will fit into their deadlines. So in this case, EDF is clearly the better scheduler. The real-time database system's efforts to schedule transactions such that the greatest number of transactions commit before their deadline can be fruitless if the operating system doesn't provide appropriate support. To illustrate this, we executed real-time database transactions on Mac OS and on a real-time operating system, DOS, from DDCI. In the first test, with read-only database transactions of equal priority and the EDF scheduling policy, 12% of the transactions on Mac OS were aborted, whereas no transactions were aborted with DOS. In the second test, with a higher priority task and a transaction writing to the database, and a lower priority task and a transaction reading from the database, 1.5% of the write transactions and 12% of the read-only transactions on Mac OS were aborted. Under the RTOS, only 0.08% of the write transactions and approximately the same number of read-only transactions, 13% in this case, were aborted. Again, 1.5% of the write transactions under Mac OS were aborted versus just 0.08% under the RTOS. These results are because an RTOS guarantees the CPU budget that's allotted to a task. With non-real-time operating systems, the time allotted to tasks is a suggestion, not a guarantee. So wrapping this up, I hope I've done an adequate job of explaining that the responsibility of a real-time database system encompasses that of a conventional database system's responsibility to maintain internal consistency, but expands to include the responsibility to maintain consistency with the real world. In other words, external consistency. I hope I've also highlighted that real-time doesn't mean real fast. The metrics used to measure real-time and non-real-time database systems not only are, but they must be different. We've learned that the database transaction scheduling policies for real-time systems are not a one-size-fits-all proposition. You need to understand the operational characteristics of the real-time system and choose or implement a transaction scheduling policy that will maximize the number of successfully committed transactions versus those that are aborted to avoid missing their deadline. Last, we've just seen that an RTOS is necessary to get the full benefit of a real-time database system. Please contact me if you have any questions or comments about the presentation or about real-time database systems in general.